Hello everyone. In this lecture video, I am going to discuss this topic called recurrence relations and generating functions. The reason why I want to discuss this topic is that recently in the first lecture video in chapter 2, I realized that most of the students already forgot the topic in calculus 3 with regards to the sequence. Okay, recurrence relations are uh, another way of defining a sequence, and recurrence relations, in order to solve it, you will need uh, generating functions, and these two are very important topic because, as you can see in the first lecture video, it's really hard to find the closed form expression of the given recurrence relation. Remember in our example 25, uh, it says there, you are going to we solve the that problem. If you remember, p sub n plus 1 is equal to 0.7 times p sub n, with p sub 1 is equal to 1 and the other one also. And I noticed that most of you maybe forgot the topic in calculus 3 about sequence. So I realized that with this, you will be able to uh, this topic will add more to your knowledge about sequence. Okay, so anyway, these two topics, recurrence relations and generating functions, are very important because to solve a given recurrence relations, you will need generating functions. Okay, so let's recall or define first what is a sequence. So remember that in our calculus 3, we define a sequence to be a function. So in this, like in this slide, as you can see, there are at least two ways on how to describe a sequence. So in here, the first bullet says here, a list of real numbers where there is a first number and a second number and so on. We are interested in infinite sequences, so our list do not end. Examples are this one, 1, 2, 3, 4, and so on, counting numbers. Or you can have this kind of sequence, 2, 4, 6, 8, 8, 8, and so on, 16, and so on and so forth. The sequences we saw in this last section, we were usually able to describe by some formula. Remember in our calculus 3, we define it this way. Okay, but as you can see, this is not always the case. The second one is when you describe a sequence using a function. So it says here a function a from the set of natural numbers to R, where we denote the output by a of n equals a sub n. This is very familiar in calculus 3. So one example is this one here. This sequence describe this first example here. This is a counting number. For the second, we have powers of 2, and this other sequence also a sub n 1 over n. This is a harmonic sequence. So it says here, any function that is defined on the set of whole numbers gives a sequence. And since we already know the definition of a sequence, there is another way on how to describe a sequence, and This way is what we call recursion. So it says here, recursion is the process of choosing a starting term and repeatedly apply the same process to each term to arrive at the following term. Recursion requires that you know the value of the term or terms immediately before the term you are trying to find. And maybe in your what do you call this subject, mathematics in the modern world, you encounter the sequence like Fibonacci sequence. Okay, that's one example of a recursion or recursive sequence. So further, it says here that a recursive formula always has two parts. So it has a first term, a sub 0, maybe two terms, three terms that are given, and then you are given the recursion equation for a sub n as a function of a sub n minus 1, maybe more than uh, one term that is given. Okay, so just like in this example, so please to remember that a recursive sequence has two parts. Okay, so for example, I will illustrate this statement here. In example 1.1, as you can see here, a sub n is equal to 2 times a sub n minus 1 plus 1, where with a sub 0 is equal to 4. So this is what I have told you, that it has a starting value which is equal to 4, and the formula, the recursion equation for a sub n in terms of the previous terms, as you can see here. And the problem with recursion equation is that you will need uh, previous values of the given sequence before getting uh, the term that you want to know. For example, if you want to know the 10th term, a sub 10, then you will need to find a sub 9, a sub 8, a sub 7, and so on and so forth, just to know the 10th term. So that's the problem with recursion equation or recursive sequence. So what we will do here is to find the closed form, and we will discuss that one later. Okay, so for another example is the Fibonacci sequence. As you can see here, you are given two starting values. We have f sub 0 is equal to 1 and f sub 1 is equal to 1. Unlike in our previous notation, we use a, but remember that it doesn't matter since it is a notation variable. Okay, so this is the set for, or the images for the Fibonacci sequence. Okay, and I know that you are familiar with this sequence. Okay, so what we will do here is we will find a closed form formula, or the explicit formula for the given recursion equation. So that's our goal, and we need generating function to find the closed form expression of the recursion equation. So, but before that, let's define what do we mean by linear uh, recurrence. Okay, it says here that if the next term is a sum of integer multiples of earlier terms, then the recurrence is a linear recurrence relation. Further, if the earliest term used to compute a sub n is a sub n minus k, that is, the previous k terms are used to compute the next Then the order of the recurrence is k. A recurrence of order k needs k initial terms to define it completely. So meaning to say, to determine the order of the given recurrence relation, it should be, uh, what do you call this one? It should be expressed in earliest term, a sub n minus k. For example, these are the example. Fibonacci sequence is an example of a linear recurrence relation of order 2. Since, as you can see, our a sub n is expressed in terms of k previous terms. Our k is 2, as you can see here. So Fibonacci sequence is an example of a linear recurrence of order 2. For the second sequence, a sub n, this is also linear of order 2, though as you can see here, there is a constant after the n minus 1, the first term here. Okay, so n minus k is, our k here is 2. Okay, the largest. The sequence is of order 1, expressed in this form. This sequence is of order 3, though there is no n minus 1 term here. The highest is k is equal to 3. Okay, it says here a recurrence of order k needs k initial terms. So in this example, you will need 3 terms, initial value, before you are going to evaluate the uh, a before you are going to evaluate a sub n. Okay, this recurrence relation is not linear. Notice that based on our definition, it is a sum of integer multiples of the earlier terms. Okay, and notice this is not a sum, but this is a product, so this is not linear. Okay, this is also not linear because it says here it is a sum of integer multiples of earlier terms. This is not linear. This is an example in, this is our example in example 25. If you remember, p sub n plus 1 is equal to 0.7 p sub n raised to the power of 2. Okay, just replace n by n plus 1 and you will get example 25. And there's a constant which is 0.7 there in our previous lecture, lecture video in part 1. Another, a sub n is equal to, this one here is linear but not homogeneous. It is because there is a constant here. Okay, so the last one, this is linear, uh, but the coefficients are not constant. So we have the coefficient here n, which is n. This is linear. This is linear but homogeneous. This is inhomogeneous. And it says here also various forms of recurrence for the same sequence. For example, this sequencer 0, 1, 2, 3, 4, 5, 6, you can express it this way. The same sequence, the same formula, but the output or the images are the same. So for example here, a sub n is equal to n. This is not linear. Okay, this is not linear. This is linear but not homogeneous. Okay, when n is equal to 0, so we have here 0. When n is equal to 1, we have here 2, 3, and so on and so forth. And as you can see, they are just the same output but different in formulas, and you will see that it will generate the same numbers, okay, if you use this formula. And also this formula also, uh, it is a linear of order 2, but the same as the image are the same as the previous two. Okay, so it may be that the formula are different, but the output are the same. Okay, so this is what we mean by various forms of recurrence for the same sequence. Okay, these are the classification of recurrence. So recurrence type, first order, this is an example, linear, non-linear, this form, linear but homogeneous, non-linear if you have a fraction or multiplication involved. This is second order, this is linear, non-linear, since we have a square root something here and a product. Uh, Variable coefficient, we have also here, 50th order, and so on and so forth. So these are uh, classification of recurrence relation. So let's go now to this slide, and what we will do here is uh, if you are given a recursive sequence, so how will you find the closed form or the explicit formula of the given recursive sequence? As I've said before, if you are, for example, this one Fibonacci number, if you are given a recursive sequence, and if you want to find the example, the 10th term of the Fibonacci sequence, first, second, third, fourth, fifth, sixth, 7, 8, 9, 10. So f sub 10 is 55. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the f sub 10. I'm sorry, f sub 10 is 89. So if you want to get the 10th term or f sub 10, then you will need the previous term if you are using the uh, recursive equation of the Fibonacci sequence. So what we will do here, if you are given another example, if you are given uh, if you want to find f sub 1000, so you will need the 999 term, all those terms to get the digit that you want to determine, okay, the term that you want to determine. So in this lecture, uh, we will going to find the formula, explicit formula for the given recursive sequence or the closed form. Okay, so what do we mean by the closed form? It says here in mathematics, a closed form expression is a mathematical expression that uses a finite number of standard operation. Finite number. Okay, remember this word here. It may contain constants, variables, certain well-known operations like this one, functions and truth exponent, logarithm, trigonometric functions, and so on and so forth, but usually no limit differentiation or integration. The set of operations and functions may vary with author and the context. So for example, this this expression here is a closed form. Okay, it is a closed form expression. Why? Because there's only a finite number of operations. 5 times log x. We have multiplication, log number 2, and then we have division, we have square root. So you only have 4 operations needed to evaluate. So this is a closed form. Okay, so this is an example of a closed form expression. So for another example, if you have this equation 2, so summation of x over 2 to the I, where I starts from 0 to infinity, this is an infinite sum. And as you have noticed, this is not a closed form because it involves an infinite number of operation. So remember that this is infinity, so although it is a sum, but since it involves infinity here, then uh, based on the definition, this is not a closed form because it is said here that it should involve a finite number of operations. So suppose we need to evaluate 2, we can possibly perform an infinite number of calculations. One solution is to use our knowledge in calculus to rearrange 2 as in this form. So instead of using this expression, all you have to do is to use this, and they are equivalent. So this is the closed form expression of uh, equation number 2, this one here. So we are very fortunate that there is a simple uh, closed form of this formula here. In that case, we may seek a numerical solution instead. So what do we mean by this? Notice that since this summation involves infinite number of operation and we cannot go on forever, then what we do here is we will have a numerical solution. So the numerical solution of 2 by approximating up to 10,000 addition. Okay, not 10,000, it is 10,001, and also we have a division of 10,001. Okay, so and then you will have a numerical solution of this one here. So what do we mean by numerical solution? It says here it is any approximation that can be evaluated in a finite number of standard operation. So this is finite, although we have 10,001 summation addition, but this is finite. And if you have a calculator or a computer, then you can easily evaluate this one. Okay, let's have more examples. We have Fibonacci numbers. This is not the closed form because it involves an infinite number of operation. Remember that our n is greater than or equal to 3, and this will move on forever. So what we will do is to have a closed form, and this is the closed form of the Fibonacci number. So instead of using this recursive definition of the Fibonacci numbers, all you have to do is to use this one, and to get the closed form of the recursive equation, you will use the generating function, as I've said before. Okay, so in this one here, if you want to find the 100 term, you need the previous terms in order to get what you want to achieve. But if you use this closed form formula, then it's easy. You will not need the previous term. Just plug in n is equal to 100 and you will have the the answer. Okay, so this is what we call the Binet's formula of the Fibonacci numbers, and in order to arrive this one, you will need generating functions. Another, we have the quadratic equation. The closed form solution of this quadratic equation is given by this one, and this is very uh, easy to recall since this formula is from your high school mathematics, from your first year high school. Then you can extend it to uh, any polynomial. And also you can study more in your uh, subject in pure math about Galois theory later on. Okay. Another example we have, this is the closed form. Instead of using the summation, you will have to use this one, or summation of k. Instead of using uh, this formula, you will this expression in the left hand side, you will have to use the right hand side, and so on and so forth. Okay, that's how useful closed form is. Okay, so let's discuss now the tool on how to uh, find the or get the closed form expression of the given recurrence relation, and or the explicit formula of the given recurrence relation. So what we will need here is uh, generating functions. There are two generating functions that I am going to discuss here, the ordinary and the exponential. So definition 1, given a sequence a sub 0, a sub 1, a sub n up to infinity, the function a of x, we will denote the function a equals summation of a sub n times x to the n, where n starts from 0 to infinity, or you can use this notation, they are just the same. This is what we call the ordinary generating function, uh, and we will denote it as OGF of the sequence. And also this notation here is refers to the coefficient, this notation, uh, bracket x to the n, a of x, this is the notation for the coefficient of a sub n. For example, if the coefficient of a sub n is what they call it, no, the coefficient a sub n, not the coefficient of x to the n. Okay, so if the coefficient of x to the n is 5, so our a sub n is 5. So this is the notation. Okay, so when to use generating function. So if one day you will be doing your thesis, maybe at some point in your calculation, if you are doing number theory or combinatorial mathematics or graph theory, maybe you can use this method on how to simplify your result. So when to use generating function, it says here that first you can use it to find an exact formula for the members of your sequence. Second, you can find a recurrence formula. So meaning to say, if you are given a sequence, you can get the recurrence the closed form, and if you are given the closed form, you can get the recurrence formula. So this is related. You can also find the averages and other statistical properties of your sequence. You can also use it to find asymptotic formulas for your sequence. You can also use it to prove unimodality, convexity, and so on and so forth. You can also use it to prove identities and many other. No? So if you want to know more about your sequence, a generating function may offer hope. One example might be discovery of congruence relations, which will be discussed in number theory. Another possibility is that your generating function may bear a striking resemblance to some other known generating function, and that may lead to the discovery that your problem is closely related to one another, which you never suspected before. So this is how beautiful the idea of generating function. It is also noteworthy that this way you may find out that the answer of your problem is simply related to the answer to another problem without knowing formulas for the answers to either one of the problems. So I recall before when one of my student in his thesis used this approach to find the uh, explicit formula or the closed form formula of his output or result. So these are the generating function operations. So you are given two generating functions, a of x and b of x. The difference is that for a of x, the sequence is a sub n, while b of x, the sequence is b sub n. Then one can perform a number of simple transformations to get generating functions for other sequences. And it is the dot operations are shown in figure 1 and 2. So this is not the figure, this is somewhere here. Okay, but before that, let me give to you, I know you are very familiar with this sequence here, 111. So this is the ordinary generating function of this sequence. So if you are given a sequence like this or this one, these are the uh, generating function of the given sequence. And also if you have this one here, this is a very nice uh, sequence, and this is the corresponding generating function. And also this one, I know that you are very familiar with this uh, what they call this one in a power series. So this is the equivalent sequence, and this is your generating function, and so on and so forth. Okay, for the operations, you can use, we will use this one later when we try to get the, what they call this one, the closed form expression of uh, the given recurrence relation. Okay, these operations are very important. You can do right shift, left shift, this one here. I will illustrate this one later. You can use also scaling, index divide, integration, or index multiply, differentiation. As you can see here, we have multiplication, left shift, we have this one, right shift, and we can also have addition, difference, convolution, and partial sum. So these are the operations on ordinary generating functions. They are just the same if you are going to use exponential generating function, as we shall see it later. So this is for the exponential. They are just the same as the ordinary. The difference is that this one here, we have over n factorial. Okay, so there's a difference between exponential and ordinary. So that's the only difference here, n factorial, and the same, almost the same definition. Okay, this is for the exponential, the same sequence as before but different form when you are using the exponential generating function. As you have noticed, we have the sequence 111. You can, the generating function uh, is used is this form, but if you look at on our previous discussion, we have this one here. This is just like the geometric, I don't know if you recall, geometric sequence, geometric power series, sorry. Okay, so this is for the exponential generating function, and this is for the operations on exponential generating functions. We will use this one later. Okay, there's also a right shift or left shift for what you call this one, exponential. There's also for the ordinary. Okay, so okay, in this slide, how to use generating function to find the solution of the recurrence relation. Okay, this is the step. So if you are given a recurrence relation, not the closed form but the one that we discussed before, what we will do here is first we have to multiply both sides by x to the n. These are the steps. Evaluate the sums to derive an equation satisfied by the OGF. Solve the equation. Express the OGF as a power series to get expression for the coefficients. And the same method for the if we use OGF with EGF. Instead of using uh, in OGF we multiply x to the n, in EGF we multiply x to the n over n factorial. And before we try to solve this example here, let me give a reminder. This reminder will give you a hint on how on where on what to use either OGF or EGF. So it says here it is not always clear whether an OGF or an EGF will lead to the most convenient solution to a problem. What do we mean by this? This means that you have to work hard or you have to try hard, try to solve as many as you can, uh, as many recurrence relation or given recurrence problem in order to make use of this method OGF or EGF. It says here sometimes one will lead to a trivial solution and the other to difficult technical problems. Other times either will work well. So maybe if you use OGF, you will the given recurrence will be hard to solve and easy for EGF, or maybe easy for EGF and it's hard for OGF. So what you will do is practice, no? Makes at least try 100 problems so that you may be well versed on how to use OGF or EGF. So for now, let's try to apply the lecture on how to find the closed form of the given recurrence relation. So for the first, there are 5 here. There are 5. I'm going to solve it, maybe 3 of these, and then I will give also a problem set, an assignment, and of course there will be a question in Edpazo with regards to our lecture. So let me first solve the first problem using generating functions. Okay, welcome back. So this is the solution of example 26, letter A, and as you have noticed, there are 5 problems that we are going to solve, or maybe 3 that I'm going to solve. And before that, before I forget, remember the what they call this one, our previous lecture, example 25, this sequence, okay, defined recursively. we solve this one using a brute force, or I don't know what kind of method that we use, but I will call it brute force. And if you remember, in our solution, uh, as you can see before, this, I think this is the one. Okay, this is the one that uh, that we did. Okay, so maybe we can, okay, so this one here. So we solve it uh, all the way here, this portion, the closed form expression of the given p sub n plus 1 is equal to 0.7 times p sub n, and p1 is equal to 1. The closed form is 0.7 to the n. We solve it this way. Okay, and we saw a pattern. Okay, we saw a pattern. That's why we arrive at this form. So I think this is brute force, but there are problems. There are recurrence relation that that cannot be done in this method. Uh, just like uh, just like the given in where are you? This one here. This given here. This cannot be done using that kind of approach. Okay, so especially if you are given a most nonlinear recurrence relation, cannot be solved in that way. Okay, that we did in uh, part 1, chapter 2, part 1 lecture video. Okay, so but if you are going to use generating function, then that will be easier. So we will not solve the our example 25 using generating function, but instead we will solve uh, example 26 letter A, and maybe we can try more of this one, so that you will have more ways to understand the on how to use the generating function. So okay, let's start example 26 A. Okay, so let's go to our open board. Okay, and then let me open my this page here. Okay, so where are you? This one here. So let's try to solve example 26. Example, okay, example 26. Example 26. Letter A. Okay. Let me put the given first. Okay. The given is a sub n plus 1 is equal to 2. A sub n, am I right? Plus 1. For n greater than equal to 0, with a sub 0 is equal to 0. So this is the solution. Okay, so this is the solution for example 26 letter A. So let's try this color, green. First is since we are using the method of generating function, let's let uh, a of x, this is ordinary generating function, a sub n x to the n starts from 0 to infinity, or you can use the other notation. You can use this one, it's just the same, 0 to positive infinity. Remember that in this equation, our n starts at 0, since the first term is a sub 0. So maybe in what do you call this one, in uh, let's say example letter B here, not a sub 0 but this one, it starts with notice that the what do you call this one, the index is no, the order is 2, k is 2, the order, no, this letter B, example to this B, is a linear recurrence relation of order 2, this is linear of order 1. Okay, so I'm going to solve letter B, and as you have noticed later, you will encounter that in there are times that we will not start at n is equal to 0. Okay, later. So let a of x be equal to the summation of a sub n x to the n starts from 0 to infinity. Then let's go to our steps. Let's go to, where are you? Let's go to the steps here, methods, or the steps on how to solve a recurrence relation. Solve means to find a closed form. It says here that multiply both sides of the recurrence by x to the n and sum on n. Okay, so let's go to the our open board. We have to multiply this one here. Okay, this one here, we have to multiply both sides by x to the n. So we have a sub n plus 1 x to the n, and then 2a sub n 1 x to the n. Okay, so that's the first step, and then you have to sum. Okay, but before that we have to distribute. Let's distribute x to the n first. Okay, so we have here a sub n plus 1 x to the n is equal to 2 a sub n x to the n plus x to the n, and then we are going to get the sum. Okay, and starts from 0 to positive infinity. Okay, 2a sub n x to the n plus x to the n starts from 0 to positive infinity. Okay, so let's distribute the right side. Okay, this one here, let's distribute the, not that one, the summand. So what we will get here is x to the n starts from 0 to positive infinity equals, uh, let's say you have 2 here, a sub n x to the n. You can move outside the constant plus summation of x to the n, and starts from 0 to positive infinity. Okay, notice, I don't know if you notice, uh, notice that we let e of x to be this form, and the first term on the right hand side is, we know that this is equal to e of x, right? This is this one here. Let me move it somewhere. We know that let's have a bubble top here. Thought here. This is a of x. Okay, 2 times a of x. Okay, and this one here, the second term on the right hand side, I don't know if you remember, uh, the geometric power series. This is 1 over 1 minus x. Okay, I don't know if you remember. Let's go to this one here. Where are you? Ordinary. Ordinary, where are you? This one here. Okay, we use z here, but replace x by z. Okay, replace x by z. And okay, so that's it for the first term on the right hand side and the second term on the right hand side. But notice that the left hand side is not a of x, right? This is not a of x. Look at here, the right hand side. Just go back to our a of x. The our a's are the coefficient or the terms. Okay, the coefficient a sub n is of the form a sub n. However, if you look at this one, is a sub n plus 1. So it was shifted. I don't know if you recall. Is in our previous discussion, it was I know this is shifted to the, is it right or left? Okay, so let's go to our operations on ordinary generating function. So is it right or left shift, this one? Okay, this is summation of a sub n plus 1 times x to the n. Just replace x, z by x, and starts from 0 to infinity. So this is the form. Okay, this is the form a of x minus a sub 0 over z. Okay, so we will use this one. I hope you know how to use this. So a of z minus a sub 0 over, or a of x minus a sub 0 over z. Okay, so let's go to our open board, and since we know that based on the table, uh, table C, table 1 or figure 1, figure 1, figure 1. Okay, it is right shift. Okay, so let's erase this one here. Right shift or left shift. So this is a of x minus a sub 0 over x. Okay, but what if you will not believe it? Okay, so let's try to expand this one. Let's use a scratch somewhere here. Scratch paper. So let's expand a sub n plus 1 x to the n, and starts from 0 to positive infinity. So let's try to expand this one. This is a sub 0. No, when uh, when n is equal to 0, this is a sub 1 x to the 0 plus a sub 2 x to the 1 plus a sub 3 x squared. Let's try more. A sub 4 x to the 3 plus dot up to a sub n plus 1 x to the n plus dot. Okay, so this is our scratch paper somewhere here. Okay, so notice that our a of x, okay, our a of x is summation of a sub n x to the n starts from 0 to infinity, and if we try to expand this, this is a sub 0 x to the 0 plus a sub 1 x to the 1 plus a sub 2 x squared, and so on and so forth. Okay, so notice that uh, this one here starts with a sub 0. So what we will do is we are going to add a sub 0 here. Let's put uh, a sub 0 here minus plus a sub 1 plus a sub 2 x plus a sub 3 x squared, and so on and so forth. Okay, since we add a sub 0, we have to subtract it somewhere. Okay, we have to subtract here a sub 0 so that it will be equal to the original, to the given. Okay, and notice that they are just the same. Okay, they are just the same as this the given here. Okay, so let's what we will do here is to express the given into this form. Okay, so that we can show that it is equal to this one here. Okay, so notice also that we can write it in this form: a sub 0 uh, plus uh, a sub 1 x a sub 1 x plus a sub 2 x squared. We can multiply by x squared plus a sub 3 x cubed, and so on. Okay, minus a sub 0 over x, and notice that they are equal to the original. Okay, remember that if you remove the parentheses, we have a sub 0 minus a sub 0 is 0. Okay, and then a sub 1 x divided by x is a sub 1, which is equal to this one here. Okay, this one here. A sub 2 x squared divided by x is just the same as a sub 2x. Okay, so and so on and so forth. So what happened here is that we express our given to a of x minus a sub 0 over x. So these two are equivalent, no? They are, this is how you derive instead of using the table in your figure. Okay, so I don't know if you remember uh, this one here. Sorry, we have left shift. Okay, not the right shift, left shift, n starts at 0. Okay, so let's go back to our open board. Somewhere here, solution, and then what happened is that this is a very nice expression. We can write it as a of x minus a sub 0 over x is equal to 2a of x plus 1 over 1 minus x. Okay, so that's it. We simplified our given recurrence relation to this form using generating function. So let's simplify, and notice also that this is 0. Okay, this is 0, right? Based on our given, as you can see here, a sub 0 is equal to 0. So we simplify it more like this. This is a of x, sorry. This is a of x over x is equal to 2 a of x plus 1 over 1 minus x. Okay, so how do we simplify this? Let's move a of x to the left hand side, and all the variables to the other side, to the right hand side. So let's move it this way. This is a of x over x minus 2a of x. Is equal to 1 over 1 minus x, and then I guess we can get the LCD, which is x. We have a of x. I know you are very familiar with this one. 2x a of x, 1 over 1 minus x, and then you can factor out a of x. Okay, a of x times this is x, and then 1 minus 2x is equal to 1 over 1 minus x. And then you can multiply both sides by x over 1 minus 2x, x over 1 minus 2x. So we have here cancel. So what remains on the other side is a of x, and this is equal to x over 1 minus x times 1 minus 2x. Okay, so we are almost done. Next is we will use partial fraction to simplify the right hand side. Okay, use now uh, we will use, okay, partial fraction. This is our topic in calculus 2. Okay, so this is x over 1 minus x, 1 minus 2x is equal to a over, no, we will not use a since we already used that letter. Let's try b over 1 minus x plus c over 1 minus 2x. So multiply both sides uh, by 1 minus x, 1 minus 2x, 1 minus x, 1 minus 2x. Okay, so what remains here, we have x is equal to b times 1 minus 2x plus c 1 minus x. We are almost done. So we have here is x is equal to b distribute 2b x plus c minus cx, and then you have to group. Let's say negative 2b minus c x plus b plus c. Okay, and but we get these two equations. Negative 2b minus c is equal to 1, and I know that you are very familiar with this one here, is equal to 0. Just recall your partial fraction topic. So we can add, and notice that that is 0. So we have negative b is equal to 1. So b is negative 1. Okay, from this we have c, which is equal to, just substitute to one of the equation. Let's say this one here, negative 1, so c is positive 1. C is positive 1. Therefore, thus we have x over 1 minus x, 1 minus 2x is equal to, where are you? Our b is negative 1, so let's write this one first. Okay, so that we have a positive in the first term. 1 minus 1 over 1 minus 2x minus 1 over 1 minus x. Okay, so what does it say? Let's move somewhere at the top. Let's copy this one here. Okay, so let's move somewhere here. Okay, 1 over 1 minus 2x minus 1 over 1 minus x. So remember, in our power series in calculus 3, this is summation of geometric power series. Let's put it somewhere here. Recall summation of x to the n, n starts from 0 to positive infinity is equal to 1 over 1 minus x, where absolute value of x is less than 1. Okay, so let's use that idea. So our x here is, as you recall, our x here is 2x. Replace x by 2x, so we have uh, summation of 2x to the power of n. N starts from 0 to positive infinity minus this one here. Okay, that one is just this one, right? So just copy summation of x to the n. N starts from 0 to positive infinity. Okay, simplify. So we have summation of 2 to the n x to the n. Just copy. N starts from 0 to positive infinity and then let's combine the summation. This is summation of we have the same starting point, n is equal to 0, n is equal to 0, and then the variable x to the n are just the same, so we can factor out. So we have here 2 to the n minus 1 x to the n. N starts from 0 to positive infinity. Okay, so meaning to say we are almost done. Okay, we are almost done. Therefore, this is the thing that we want to get. Okay, so therefore a sub n is equal to 2 to the n minus 1. Okay, and notice that in our given where are you this one here, and our given, where are you, 1a starts with a sub n plus 1, right? Okay, so if you want to know a sub n plus 1, just replace n by n plus 1. Okay, so how to use this is the end of the solution. Okay, so if you will put a bubble thought here somewhere here, just replace n by n plus 1. So we will have a sub n plus 1 is equal to 2 to the n plus 1 minus 1. Okay, for the formula for a sub n plus 1, just like in our given here, as you can see here. So let's try to what we call this one, list the elements of this recurrence equation with one that we have that we the formula that we get in using generating function. Okay, the closed form. So let's try to substitute some values. Okay, let's try to substitute some values. Maybe let's sub somewhere here verification. let's have here verification. Our given is a sub n plus 1 is equal to 2 a sub n minus 1. Am I right? Where are you? Plus 1. Okay, plus 1. This is plus 1 for n greater than or equal to 0 and greater than or equal to 0 with a sub 0 is equal to 1. Am I right? 0. Okay, 0. This is 0. Okay, and the closed form is this one here, closed form. Let's try another color. This is our closed form is a sub n plus 1 is equal to 2 to the n plus 1 minus 1. Okay, let's try to substitute some values. Let's try this color here. A sub 1, we have a sub 0 is 0. A sub 1 is equal to 2. N is equal to 1. Okay, a sub, no, not this one here. I'm sorry, but I made a mistake. Okay, this is 1. N is equal to 1. We have a sub 2 is equal to 2 a sub 1 plus 1. So this is our, what is a sub 1? There's no a sub 1, so let's try, I'm sorry, let's try say 0 first. A sub 0. Okay, and this will become, sorry, I made a mistake again. This is a sub 0. A sub 1 is equal to 2. So that's the problem if you are using recurrence relation. So you need the previous term, a sub 0 plus 1. So this is 2 times a sub 0 is 0. Okay, plus 1 is equal to, this is 1. Okay, so when n is equal to 1, this is a sub 2 is equal to 2 a sub 1 plus 1. So this is 2 times, or a sub 1 is 1 plus 1. So this is 3. Okay, let's try more. N is equal to 2. A sub 3 is equal to 2 a sub 2 plus 1. 2 times, what is a sub 2 is 3 plus 1 is equal to 6, 7. 2 more. A sub 4 is equal to 2 a sub 3 plus 1 is equal to 2 a sub 3 is 7 plus 1 is equal to 14, 15. Okay, and so on and so forth. Okay, that's the first 4 terms. So how about if we are using the closed form? What do we have here? Okay, do they have the same image or output? Let's try this color green. N is equal to 0. A sub 1 is equal to 2 to the 0 plus 1 minus 1. So this is 1. Okay, 2 to the 0, 0 plus 1 is 1. 2 to the 1 is 2, minus 1 is 1. So for a sub 1, we have a sub 1 is 1, okay, the same as this one here. A sub 0 is just given, okay, which is this one here. A sub 0 is equal to 0. Let's try n is equal to 1. So a sub 2 is equal to 2 to the 2 plus 1 minus 1 is equal to what? 2 to the 3 plus minus 1. So 2 to the 3 is 8, minus 1 is equal to 7. So we have here the same. Okay, sorry, did I made a mistake? This is 1 here. Sorry, this it should be 3. Okay, let's go back. 1 plus 1 minus 1 is equal to 2 to the 2 minus 1 is 4, minus 1 is equal to 3. Okay, so the same as this one here. Okay, n is equal to 2, a sub 3, 2 to the 2 plus 1 minus 1 is 2 to the 3 minus 1, 8 minus 1 is equal to 7, which is the same as that one here. Lastly, n is equal to 3, we have a sub 4, 2 to the 3 plus 1 minus 1 is equal to 2 to the 4 minus 1 is equal to 16, minus 1 is equal to 15. Okay, it's the same. Okay, and so on and so forth. So what we did, we verified that our formula is correct. Okay, so this is in our calculus 3. It is already written in what they call this one, closed form in calculus 3, but in numerical analysis we are given a recurrence relation. So that's why we have to get first the what they call this one, the closed form, in order to use the you use definition 24. If you remember our previous definition, definition 24, the variation of definition 24, you will need to get the limit, the p there. Okay, so I don't know if you remember, let's say, let's go to our definition, this top monitor, this one here. And if you remember our definition 24, where are you? Definition 24, this one. Okay, we discussed this before, and we need the limit of the sequence. But if your sequence is defined recursively, then you cannot get the limit by solving the recurrence definition. Okay, the given is in recursive form, so you cannot get the limit directly. Okay, so that's why you have to find the closed form first and then get the limit p in order to use the other variation. Okay, so if you remember the other variation, where are you? Let's go to open our open board, and let's open this document here before. Where are you? I guess this one here. Where are you? I don't know what happened, but this one here. Let's open this one here first. Okay, this one. Okay, if you cannot get the limit of the sequence, then it's hard to evaluate this one. Okay, to find the order of the convergence. Okay, so that's it for example 26, letter A. That's one way on how to use the generating function to find the closed form, and it's so much fun, no? That's a very nice way of solving a uh, recurrent relation to find its closed form. Okay, I don't know if you uh, feel refreshed after solving, but for me, I really like how the things work. Okay, so let's look at our example, and honestly, uh, the solution is more beautiful than using the brute force. Okay, this one here, I don't know if you remember this one, using the brute force. Okay, so probably you can uh, use generating function to find the closed form, not this using this kind of method. Okay, this method. Okay, so but how about for B? Okay, this is solution for A. So if you are going to use brute force, you can solve it, but there are times that the generating function will not also work. So it depends. So just make use of just try to solve as many as you can in order to familiarize on how to use uh, those method that I presented in this subject. Okay, thank you so much for listening. Maybe we can go now to uh, to letter B. This one here. Let's try to solve this using generating function. Okay, so I'm going to end it here and then go back.